In a tropical paradise with beautiful coastline, spectacular landscapes, ancient towns, and a thriving culture, there's a hidden force that has shaped it all. Looming in the background is one of the largest volcanoes on Earth, Mount Teide on Tenerife in the Canary Islands. But why does a massive volcano exist here in the middle of the Atlantic? And could it erupt again? Teide is Spain's highest peak at 3,700 meters and the third tallest volcanic structure on Earth when measured from the ocean floor. It's nearly 7,500 meters. It is massive. Today, I'll take you on a brief tour of Mount Teide, where we will look at what gave rise to it, some of the characteristic rocks in the caldera, views from the summit, and a look at some of the unusual pyroclastic flow structures. Unlike Hawaii or Iceland, the Canary Islands ocean hotspot behaves differently. In Hawaii, we have mostly fluid basaltic lava creating shield volcanoes. In Iceland, we have both hotspot and rift valley volcanism due to its location on a spreading center. In the Canary Islands, we have more explosive volcanism with a mix of basaltic and phonolitic lavas, large-scale cone collapses, and pyroclastic flows. We'll see some of these rocks up close. These islands are one of several mantle plume systems beneath the African plate that has been active for over 20 million years. The road leading to the volcano drops you right into the caldera. This is the Las Cañadas caldera and is about 16 kilometers wide and was formed by a series of eruptions and collapses over the last 1 to 2 million years. These collapses were triggered by massive explosive eruptions, leaving behind thick ignimbrite deposits on the flanks of the volcano. Ignimbrites are a rock made from the ash and pumice of a pyroclastic deposit, so they can be welded or not. Some of the cinder cones inside the caldera formed after the collapse, hinting at continued volcanic activity through multiple vents. Views from space show just how many different kinds of flows there are and how extensive they can get. The colors you see represent the chemistry of lava from different depths as it made its way from the mantle to the surface. The dark lava flows are relatively young, mostly from Teide's last eruption in medieval times around 1150. Unlike Hawaiian lava, Teide's phonolitic lava is viscous due to its high silica content causing thick, slow-moving flows, and you can see a number of ripple marks where lava was piling up and pushing material downhill. The summit offers a 360 view of the entire caldera, showing the scale of past eruptions. As you work your way around the caldera, there are a number of stops where you can look at the different lava flows. Many of the boulder fields will have a variety of materials, some of which may have traveled through erosion, particularly if the boulders are rounded. Fine grain basalt, very dark, very black. It's also got some remnant vesicles, gas bubbles. But yeah, the field is chock full of all these materials. Similar basalts near the summit have black lavas with white crystals of plagioclase. Below, some of the lavas have almost a glassy texture, and in one case, folds corresponding to flows that are piling up. So once the volcano has degassed, what you're left with is a very viscous, thick flow, and these are some of the chunky rocks you see behind me. This is the stuff that came out in the last part of the flow off one of the summit eruptions. In here you see a few pumice fragments, a lot of limonite or iron oxides to give it the reddish color. And if you break the rock, yes, you can see the very dark black inside basalt. While looking for interesting features on the island, I came across an unusual outcrop that I first thought might have been associated with soft sediment deformation. Yet this was not a sedimentary deposit. Nor was this an unusual outcome of multiple pyroclastic flows, since I did not see welded ash, even though this middle layer was fairly white. Upon closer inspection, however, it turns out that this is actually an example of meteoric or groundwater alteration and chemical weathering. Volcanologists who work on this island have identified these curious features as a result of weathering and chemical alteration of minerals within a brecciated lava flow. So let's go through how this forms. As lava moved over the landscape, the basal layer fractured as it came in contact with the cooler ground surface. At the same time, the upper part of that flow also brecciates as hardened crust forms and breaks apart while the lava continues to move. If two successive lava flows are deposited, they can create an intermediate zone of breccias that is highly porous and permeable, just like we see here. Eventually, most, if not all, the flow fractured into a breccia as it moved across the landscape. You see the volcaniclastic fragments when looking at this outcrop up close. Over time, slightly acidic rainwater infiltrates the breccia. You also have groundwater that worked its way into the flow. The porous, brecciated layers between flows acts as pathways for the water, allowing deep chemical alteration with very irregular patterns like the flames that you see here. And you can see signs of chemical alteration down to the mineral level. The alteration likely involves the formation of carbonates, smectite, which is a type of clay and often white, and zeolites, which are common in basalt weathering. This is a great outcrop for further petrographic studies and to show students the power of subsurface weathering. Throughout the island, you can find a variety of pyroclastic deposits that include fine ash flows, pumice, and a host of volcanic glasses. Some appear to be welded, while others appear to be somewhat chemically altered. The distribution of these deposits throughout the island are a reminder of just how explosive and violent the eruptions were in the past. So if we step up to a road cut and look at a close-up of these flows, you can see the variety of material in here. A lot of it's very crumbly as it erodes, but it's all that ash. A lot of these were strombolian eruptions, so there's a variety of different fragments coming out. And some of these larger bits are very light pumice. Looked out on the weather, sometimes it's pretty windy up here, and you can't get up here, or at least they close off a lot of the mountain for any visitors. Time to head down as the altitude is starting to hit me. As I head down the mountain, you can't help but contemplate future events, particularly in terms of the hazard that they represent to population centers. Yes, they are inevitable. When? Who knows? But the occasional seismic events and gas emissions suggest that there is still magmatic movement below Teide. However, many scientists believe that it's approaching the end of its life cycle and will not generate the scale of massive eruptions that it generated in the past.